Hi, I'm Nathan Stovall, and I'm a sophomore chemistry major here at the University of Oregon. I've had the privilege of working in the Betcha Lab under the guidance of my mentors, PhD candidate Rana Kravina and Dr. Shannon Betcher. Our work revolves around the development of a low-loading iridium catalyst for the oxygen evolution reaction in acid. With an increased global demand for clean energy, the use of hydrogen as fuel produced via water electrolysis, or water splitting, via a water electrolyzer has been of high interest. More specifically, the state-of-the-art proton exchange membrane, or PEM, electrolyzer has shown a high degree of promise, but is limited by the rate-determining oxygen evolution reaction, as well as the low abundance of iridium, the only OER catalyst known to be stable under the harsh conditions of PEM electrolysis. To this end, we've worked to develop and characterize a low-loading iridium catalyst supported on a cheap, acid-stable metal oxide support while maintaining high activities. This led to the development of a simple synthetic method in which we soak antimony-doped tin oxide nanoparticles, or ATO, in an organic solvent with this iridium dimer we call IrCOD. UV-vis data suggests that this binding mechanism is surface limited, which can be seen as the absorbance plateaus after about 2.5 hours, showing iridium is no longer adhering to the surface of the metal oxide. This is likely because the reaction is limited by the surface hydroxyl groups of ATO. Then, using a model metal oxide, triphenylsilanol, nuclear magnetic resonance spectroscopy was used to track the hydroxyl hydrogen of the metal oxide before and after reacting with the IrCOD. In the reactive product, the presence of this hydrogen was still observed but was slightly shifted, suggesting that our iridium dimer is likely binding through electrostatic interactions as opposed to displacing the hydroxyl hydrogen. One working hypothesis is that this may be occurring through the partial positive hydrogens and the partial negative chlorine of the dimer, as shown in the figure here. We also developed an iridium calibration curve to determine the loading of our catalyst on our electrodes. This is done using X-ray fluorescence spectroscopy, where we can relate the peak area of the XRF data to the mass of the catalyst. This allows for quick determination of mass loading and a means to compare our catalyst to other iridium catalysts as a function of mass. Next, to test the electrochemical performance of these catalysts, we ran cyclic voltammetry experiments, where we swept between a range of potentials and monitored the current response in terms of mass activity, which is the current per unit mass. The earlier the onset of the current is indicative of OER onset. We see our novel catalyst has significantly higher performance when compared to the state-of-the-art iridium oxide nanoparticles at a reduced mass loading. This is likely due to the fact that higher loading catalysts have many of their active sites covered up, decreasing the performance. We also observed catalyst segregation, seen here on the right, likely due to the iridium only attaching to the metal oxide surface via electrostatic interaction, causing them to degrade. This leads us to our future directions and where we plan to take the project. We want to compare the dimer's activity to existing molecular OER catalysts with oxidatively stable ligands to see how those impact activity and stability. We also want to conduct ICP-MS analysis for dissolution quantification to see if our iridium, or ATO, is falling off the surface of our electrodes. And lastly, we want to test different reaction conditions to facilitate stronger binding interactions with the metal oxide support. And lastly, I want to say a huge thank you to the Betcha Lab for allowing me to work in their space and being so kind and so helpful, giving me tremendous opportunities, as well as to the Phil and Penny Knight campus for accelerating scientific impact, for giving me the incredible honor of being a Knight campus scholar. Thank you.